Today we're going to talk about Dalton's law of partial pressures. Let's think about air. Air is a combination of 78% nitrogen, 21% oxygen, and 1%, let's just call that other. So in terms of the pressure, if we talk about air at sea level, 1 atmosphere of air, the different constituents in the air contribute to the pressure. So if it's 78% nitrogen, as far as the particles are concerned, which is also the volume, and the nitrogen contributes 78% of the pressure. So you have 0.78 atmospheres due to the nitrogen gas, and you'll have 0.21 atmospheres to the oxygen gas, and you'll have 0.01 atmospheres, all the other gases combined. If we look at a container and we have some particles in there, let's just say these are nitrogens. So they're bouncing around off the walls, they're making pressure. And then I have another container. Okay, there's some oxygen particles in this container, and they're bouncing off the walls and whatnot. They're exerting pressure as well. If I combine these, put them together into one container, let's have the nitrogen gas, so with its 5 particles, and the oxygen gas with its 5 particles. What's going to happen to the pressure in this if I combine the two gases with it, so that however many particles were in this container plus however many in that container end up over here? So this is exerting a pressure of 0.4 atmospheres. Let's say if we have the same number of particles, this one's also exerting 0.4 atmospheres. What's going to be the pressure of the container over here that has both the particles combined? All these particles are going to be bouncing off the walls now. Now I have twice as many particles bouncing off the walls at their different speeds and with their different masses and whatnot. If I took the 5 particles there and the 5 particles there, and then this one would have twice the pressure. And that's essentially Dalton's law. Dalton's law says that the total pressure of a mixture of gases is equal to the sum of their partial pressures. This can be written mathematically as P total, which is the container or whatever pressure we're considering is equal to. This is a Greek character for capital sigma for sum of partial, P partial. For us, the simple case is that the pressure total is going to be, for this mixture, is going to be equal to the pressure of the argon, the partial pressure of the argon, the pressure that it exerts inside the container, plus the pressure of the neon, the pressure that it exerts. And in general, the P total is equal to P1 plus P2 plus however many gases are in the container. So I've given you kind of rules for each one of the, like the combined gas law, remember there's a change. For the ideal gas law, there's no change. They give you 3 states, you find the 4th property, pressure, volume, temperature. For this, the tip-off for this one is you have a mixture of gases. And not just a mixture of gases, but you have a mixture of gases and there's no chemical reaction. The first step would be to assign variables. That's kind of what we've done with all the gas laws. Remember, we find P1, V1, P2, V2, that kind of thing. Choose the best equation. So actually with Dalton's law, we get a couple choices. There's one choice is the P total is equal to P1 plus P2, ... The other one is for P total equals N1 plus N2, the moles of the first gas plus the moles of the gas, second gas plus ... however many gases times RT over V. Then step 3 is to rearrange the equation to solve for what you want. A lot of times you might be solving for the total pressure, but other times you might be solving for P1 or P2. What I've always taught is use the formula, isolate the variable, then plug the variables in. Plug in and solve. 5. Make sure units cancel, right? They should cancel and they should give you the unit you want. And finally, think about significant figures. Make sure, does it make sense? You can kind of do an estimation to decide if you calculate it properly. So I have a 100-watt light bulb in a light bulb with total pressure equals 111 kilopascal. The argon has a pressure equal to 102 kilopascal. What is the pressure of nitrogen gas if the bulb only has argon and nitrogen? So variables, P total equals 111 kilopascal. Pressure of argon equals 102 kilopascal. Pressure of nitrogen equals question mark. For me, the best equation would be the simple one. P total is equal to P argon plus P nitrogen. Then I want to rearrange. How would I get the partial pressure of nitrogen by itself? Would I multiply or divide? I think I would subtract. So this, because it's a sum, and then you're going to subtract. I'm going to subtract the partial pressure of argon from both sides. P partial pressure of nitrogen is equal to P total minus partial pressure of argon. And now I'm going to plug in my variables. So since I'm doing a sum, they have to have the same unit. So I'm not really canceling units per se, but I got to make sure they're the same. 111 kilopascal minus 102 kilopascal. I say I get 9 kilopascal. Interestingly, this was a subtraction, but we had 3 sig figs here and 3 sig figs here. We're going to end with 1 sig fig. That can happen. Let's do a harder one. In an 85 milliliter light bulb, you have 0.140 grams of argon and 0.011 grams of nitrogen at 20 degrees Celsius. What is the total pressure in the bulb? All right, so let's assign variables. So what's the mass of argon? I have mass of nitrogen, volume, temperature. So they didn't give me pressure at all, but yet they want pressure. So what does that kind of lead me to? So let's write these out. So 0.140 gram, 0.011 gram, 20 degrees Celsius, and 85 milliliter. So after assigning the variables, I think the equation that I want is that the P total is going to be equal to the moles of argon plus the moles of nitrogen times RT over V. What we have for the homework is this equation or this one. And so if they give you the pressures, then you probably use the first one. If they don't give you the pressures, then probably use the second one. They didn't give us the pressures, so we have to use this. Are the units okay? Can I just use 85 milliliters? No, I want to change that to liters. I'm going to divide by 1,000 and get 0.085 liters. And then the temperature, I want to add 273.15. So temperature will then be 293.15, accurate to the ones place. The volume would be 0.085 liters. I still need to find the moles of argon and the moles of nitrogen, so that's a little work too. I have 0.140 grams of argon, and the molar mass of argon on my periodic table is 39.95 grams of argon to 1 mole of argon. That would be, so it looks like I have 3 sig figs, 0.00350. There's a 4 after it. I'll just put the 4 there, but it's 3 sig figs. And I also have 0.011 grams of nitrogen, and my molar mass of nitrogen, 28.02 grams. This is going to be 0.0003925. And this is only 2 sig figs. I'm going to add these. Moles of nitrogen plus moles of argon would be equal to 0.0038965. And so I think I still get to have 3 sig figs because this one is the 100 thousandths place, and this one's the place I underlined, there's also 100 thousandths place. I get to be accurate to there. P total is going to be equal to the N total times RT over V. So it's going to be equal to 0.0038965 mole total times gas constant, which is 0.082058 liters times atmospheres over moles times Kelvin times the temperature. So it was 293.15 Kelvin, and all of that divided by the volume of 0.085 liters. How many sig figs should I have? Because of the volume, I'm only going to have 2. And I get P total 1.1 atmospheres. And that sounds reasonable. So like the pressure of a light bulb is just a little bit more than atmospheric pressure, basically. So that is essentially Dalton's law.